fantastic for you so far. I've learned a lot just checking the references I sort of come up with. But I want to give you an experimental view of maybe a new system, which is not graphene and it's indium arsenide. And it has advantages and disadvantages, but I think one thing that we have learned in the last few years that has a great advantage is making good contacts to indium arsenide. And maybe this topic kind of benefits from this extra advantage. So the work that we've done, the experimentally at NYU was the work of my graduate student, Mehdi Hatefipour. And this was in collaboration from the theory from College of William and Mary and help for nanofabrication from Sandia Lab. And we have collaboration within NYU and University of Arkansas. Today, as it was requested, I will just stay with experimental facts. So just a quick background and motivation. I did my PhD in quantum Hall effect and in gallium arsenide. And the goal, one of the good goals, I guess, there was to kind of find these Moorhead states or Pfaffian, anti-Pfaffian states around 5.5. And indeed, if you have a really good MBE, a really good low temperature system and push the limits, you can get samples that are in excess of 20 million mobility, and you can see 5.5 and 7.5. And the idea was to control these states. The idea was to kind of find out what is the nature of the ground state. But it's very delicate in the sense that you try to gate these things, things fall apart. And that, to my understanding, still is a great challenge and is a great problem to attack. But there is an equivalent picture, I think, which was proposed around 2012 to 2014, that if you bring a superconductor and that basically can interact with an integer quantum Hall effect, maybe a similar physics can be created, which was alluded to by Bineker earlier on, that this is a Majorana fermion. And in some particular case, you make it more exotic with fractions, it could be parafermion. But then for integer quantum Hall effect, the requirements are much lower. I don't need a 20 million mobility sample. I can live with 10,000, 20,000, 100,000 samples. So in terms of the material growth, we can, it opens up path to other materials, but now we have to ask the question, which materials can actually interface with superconductivity? So in the last 5-6 years, I've worked on indium arsenide quantum wells, and indeed, they are not as good as other materials. So let me actually show you a quick review I did in 2014 on various materials that actually have shown fractional quantum Hall effect. And if you just focus on the disorder parameter or lambda level broadening, most of these materials have already shown some sort of a fractional state. But indium arsenide hasn't. And the question we were asking is whether this is disorder related or not. And if you compare the disorders, they're not really off. It's 0.05 versus 0.025, where the first gallium arsenide 1/3 was observed. It's just a factor of 2. Whether we can sort of jump over this limit or not, I think that's a discussion for material science and maybe a more focused talk. I think it is possible. But what I just want to show is that there is disorder, but it's not like a killer in the game. The materials we discussed today are basically this surface quantum well. So we sacrifice mobility and quality for the best contact we can achieve. And it turns out, if you go back, you can actually, in 2015 and 16, it was developed in the context of Majorana fermion that you can actually make epitaxial contacts to the semiconductors. In particular, aluminum was a great match that basically we could find this domain matching to indium arsenide InGaAs structures. And if you ask, what is the quality of indium arsenide, you can see a quantum Hall trace on the right-hand side of this graph. That RXX as a function of fields shows various integer states. As we discussed, there is no fractions. Temperature is taken at 20 millikelvin. And the quantum well is very near the surface that when we put the aluminum on, you can actually get a lot of coupling. And to prove that, we have made a lot of Josephson junctions in the last few years. And you can see supercurrent, you can fit transparencies to this. And the transparencies are very high. I mean, I don't want to say unity, but it's extremely high, and I think it probably has a record in terms of what can be achieved in super semi materials. We have measured induced gaps. We did it in Charlie Marcus's lab back in 2016. In my lab, we have done it on multiple devices. And the way the gap looks like on these structures, they are hard. It's just not about seeing a supercurrent in the Josephson device. So all I want to say is that the contacts are pretty established, and we know how they behave. For quantum Hall effect, obviously that's a different game, right? I mean, you want quantum Hall but you also want something that supports superconductivity. And in this case, we need to go to niobium thionitride structures, right? So let me tell you how we make this. So we start with aluminum on indium gallium arsenide. That interface is very pristine. We go ahead and expose part of this InGas to actually make our hall bar. When we put the system into the sputtering, around exactly at that point, we actually get the aluminum off and we put niobium thionitride. So this is already done in a controlled environment. After the etch of aluminum, the surface is not exposed to air. And when we put niobium thionitride, then you can basically go ahead and put an aluminum oxide and a gate on top. So that interface is pristine. It's not epitaxially pristine, but it has not seen air, at least in the usual sense that we expose it to the ambient, right? So then this is sort of a optical image of the device. So there is a hall bar on the left side. There is a niobium thionitride on the right side. And you can basically send current from left to right, measure hall data or across the interface. The dimension is large, right? So the width of this hall bar is around 150 micron, right? In the previous devices that you heard, I think in the first talk, the contact is about 100 nanometer. In the second talk, dimensions are about a micron or two. So this is in a very long interface regime, if you will. So we looked at one of these devices at the beginning and everything made sense. So what I'm showing you here, the schematic is shown on top. So basically we are sending current from pin contact 1 in a normal contact to 4 on the right side, which is basically a superconductor. We sync the current there and we measure 6 and 5, which is normal contacts, right? We see the behavior that we expect from quantum Hall system. So if I plot sweep magnetic field on the y-axis and sweep the gate voltage or density on the x-axis, you basically go through this quantum Hall states and the zero resistance basically say, that this is a well-developed states. And if you basically get an RXY equivalent of this, we can actually mark the filling factors. So that's how we are basically saying for 812 to 610, right? And then we measured the interface, which basically we were very surprised, right? So if you measure on that schematic on the top left, basically now measure across the interface, for example, was supposed to be 4 on the left graph. Now on the right graph, still we have 4. The shape is quite similar. But now if you look at the color map values of the resistance, now we are measuring almost minus 0.8 kilo ohm, right? It's not supposed to be minus 0.8 kilo ohm. I would expect like 0, like the left side. Or maybe I don't expect it if I can allow for these Andreev reflections. And the model that we have used in our paper mostly is basically just a modified Whittaker formula that instead of having just normal reflection and a normal transmission, which will in a usual case would be all R cross T equal to 1, you allow for this A to be the Andreev reflection. And then this parameter alpha comes into the game. And let me see if I have, let me just go back. So here, if alpha is basically between 1 and 2, you get a negative resistance. That's basically corresponds to the Andreev reflection being, or A being more basically not 0, right? If it's between 0 and 1, alpha becomes between 1 and 2. So you can sort of follow this picture, but let me give you more hints about the observation. So if we basically get trace cuts at 11 Tesla, so I park the magnetic field at 11 Tesla, I measure RXX in the top left that is shown in the black trace. You see that it's a normal looking quantum Hall, right? And I can basically say this is what filling factors these are. And then now I can, same setup, I just measure now across the interface and I call it RD, the downstream. And now you see blue very happily when it gets to a quantum Hall effect, it dips into a negative resistance, right? So that's kind of surprising, but maybe it still is part of this picture. So we looked at the upstream data, which would be pin numbers 3 and 4 in this graph, if you look at the bottom graphs. And you would see that the Hall data starts to deviate from what the normal RXY is. The normal RXY is shown in the bottom graph in red. The upstream is blue. Now the upstream value is lower than the Hall data, as if now the Andreev reflection basically is not contributing to the Hall data. And that indeed is consistent with this picture of Whittaker, that basically ideally you want to see a very large negative resistance in downstream and half of the conductance of the Hall data, right? So you can say, if this is due to the Andreev reflection, how can I understand this? If you look at the colorful plots that we have each filling factor at some points, right? So for each field, when I do a horizontal cut, let me just go back here. I guess here, if I do a horizontal cut at 8 Tesla, I can capture probably 3 filling factors, 4, 8, and 12, right? So for each of these fixed field, I can try to actually plot the negative values and then ask what is the slope, and the slope should be basically related to alpha, right? And from alpha, I can basically back calculate a lower bound for the Andreev reflection. And it seems, if we believe in this simple analysis, the Andreev reflection has some field dependence, perhaps, and it sort of varies around 20% down to maybe 10% as the field is increased, right? So this is basically the basic observation. And now I want to tell you a little bit about the things that we have done around this and what would be the future direction, at least in my mind. So there are a couple of sanity checks one can do, right? If I have a downstream and an upstream within Buttiker formula, if I basically do RU minus RD, the alphas should cancel out, and basically I should be back to a Hall voltage. I have to be back to RXY. And if you look at the top left, you would see that RXY data is red. Previously, RU was below the red graph, if you remember. Now that I subtract that negative resistance from the downstream, you see that exactly at the quantum Hall values, now the red and blue matches up, while when you are not in a quantum Hall effect, they deviate, which is fine, because this picture is only true when you are in the Hall regime. And you can try to plot that as a function of field, and you see within some error bars, basically we recover 1 if we ratio this subtraction to RXY in quantum Hall effect, right? So that is very reassuring that there is no funny business going on between upstream and downstream. You can also do bias measurement. I saw in one of the YouTube talks that there was some very interesting bias dependence. In our system, we have done it, and we don't observe anything drastic in the sense that when you do the bias on the lower graph, let's just look at the lower left, basically the negative resistance obviously disappears. It goes towards 0, right? At high biases. These are DC biases now. And I have made cuts on the right-hand side of that and compare it also to RXX. So you see that RXX shows these dips, and the blue line also follows that. When you basically kill quantum Hall, then these dips also disappear. So basically this negative value is also tied up to the strength of the quantum Hall in the system. So a very straightforward version of this, I guess, is that if I measure, for example, in the left graph, in the schematic, if I compare 10 and 8 versus 12 and 8, right? So basically I'm still measuring across interface, but then I basically make a longer pass across the interface. If I have a very well-defined quantum Hall, it shouldn't matter, right? There is no dissipation across that interface. So let's just focus on the minus 11.8 Tesla. And if you look at the data, the black is the RXX, the normal RXX. Is a relatively well-defined quantum Hall state. And the blue is the shorter path. And you see that basically it likes to quantize at some negative value. And then the red is the longer path. And you see that this is slightly smaller because, I mean, it still is quite quantized at the value that the blue is also quantized to. If you look at 8 Tesla, which is the top graph, things are weaker. Even RXX is weaker. So the quantum Hall is not as well defined, or the gap is not as strong. Then you see that the blue line, which is the shorter path, is deeper than the red for example, nucleus to 8, right? But for nucleus to 4, that is, the state is quite strong. Blue and red are basically on top of each other in the middle of the quantum Hall state. So basically, if the quantum Hall is strong and you basically have the edge modes, that the system just doesn't care. And more surprisingly to me, that value is kind of a set value, right? If you look at the 11.8 Tesla graph, at nucleus to 6 and 2, both values are just following each other with high precision. You can also do temperature dependence, and as what you expect is that once the RXX is lifted up, for example, here at 750 millikelvin, the interface value also is lifted up. So if you compare the orange and yellow, yellow is the hotter trace, and you see the negative value is smaller, and you can plot it. There is really not much surprise there. It just follows the quantum Hall system. So we said, look, maybe this device is special or something. So we made different devices. And one thing that we can do is that just don't care about cleaning of the interface. So just expose the sample to air and then put it back into the sputtering chamber without doing this in situ cleaning and etching of aluminum and putting niobium tinitride. So that graph, that sample measurement is on the right-hand side. The one that we were discussing is the left-hand side. So if you look at the right-hand side, you see still some quantum Hall effect with some dark blue region. Maybe the coloring was misleading. If you look at the color bar, you see that the negative resistances now on the right graph are small, or very, very small. Like if you look at the left, it's minus 0.8 to 0.8 kilo ohm. Now on the right-hand side, when the interface is not cleaned at all, you barely see anything negative. In fact, if you actually do a line trace, let's say at 11 Tesla for this dirty sample, you can see that the resistance is on the order of 8 ohm or maybe 10 ohm, right? So same procedure, same sample, same wafer, but just not taking care of the interface. So this definitely tells me that the interface is important. And the fact that we have been able to get 20%, it is a result of actually making really nice interface. So we did, actually, Antoine suggested that maybe where we ground the superconductor is important. So in the dirty sample that I just showed you data, this is the third sample, third dirty samples. So you see the data on the left is very similar. There is a negative resistance, but it's a small. But on the right side, you see that basically we ground the superconductor on pin number 8 in this particular setup. And in the next slide, I'm gonna ground the superconductor on pin number 3. So I don't know if you notice any difference. These are actual repeat of data. We took sort of the same data on the left-hand side and the right-hand side. Let me go back. It's literally the same. The measurement that we have done on the color maps are exactly the same. So it doesn't matter where you ground your superconductor, closer to the pin on top or the closer pin to the bottom. Once you are at the superconductor, basically the data is the same. So let me give you a summary and an outlook to this. So very machine-wise, and not sort of trying to be creative. So the first talk that you heard, I think it talks about small contacts. So that interface is around 100 nanometer. And that's why maybe cross-entry reflection was one of the physics that was proposed. And the system is graphene niobium nitride. The second talk by Gleb was, intermediate interface sizes is about 1 to 2 micron. And the system is graphene molybdenum. And the talk that I just gave you, it's a long interface limit, right? We have 100 microns of interface, but we also have this epitaxial or semi-epitaxial indium arsenide niobium tinitride. And remember, the magnetic lengths in all these dimensions are much smaller, right? At 8 Tesla, you have basically 10 angstrom. So what is the future? I was hoping to actually show you data on our QPC sample. So we actually make these Hall bars on the top left that you basically bring quantum Hall effect next to niobium ti. Now what I want to do is to just put a QPC exactly at that interface and basically now look at the regime that I'm on a very small interface. So if I park my quantum Hall in equal to 8, then with the QPC, I can actually let one mode inside my superconductor. In the regular quantum Hall regime, this has been done for 5F and other states by Charlie Marcus' group, Mark Kastner's, Moti Heiblum, and Amir Yacobi's, that we can basically do mesoscopic now on top of this quantum Hall system. And I think that would be a really good experiment. We have data, but I don't want to say anything about that. I mean, this work hopefully will result into more understanding of what's happening, because now I can only let one mode in a very small area, which is only like 100, 200 nanometer, and then see what happens to the tunneling regime. In our devices, we have to use HPN because the aluminum oxide changes the density of the 2-deck. So there are some sophistication with it. Something that we started, and I don't know how hopeful I am now, is these bilayers of graphene and indium arsenide that we made devices with independent contacts to see if we can induce, quantum Hall in each of them. And indeed, you can do it. But then the problem is that I don't really understand the theory and the physics of a single long junction on indium arsenide. Then I don't know what I would expect for a bilayer of that type. But those experiments and devices are also in play. And hopefully we will learn more as we go forward. Thank you so much.